Hello everyone, my name is Thinh. Today I present my paper called ZEETAD, which is about adapting machine vision language model for zero-sum entering temporal action detection. So let me introduce a little bit about the temporal action detection. So the temporal action detection aims to both localize and classify every action instant from long and stream videos. This task is challenging because its existing supervised method is training with large amount of video data to attain decent performance. At the same time, obtaining multiple annotation pairs for temporal regions and corresponding action labels per video is laborious and expensive. This will restrict the current temporal action detection works to closest learning setting. So in our method, we want to expand it into the shadow shop or open settings. So thanks to the recent achievements on vision language or retrained models, for instance, as clip. So the success is applied to the rich semantics aligned with strong visual representation acquired from web scale image text pair, and their snapshot transferability is accomplished by matching the similarity between the query text embedding and overall image features. There have been uh, several various methods that have attacked this problem, and ours and the various method share the same input and feature extraction. So for the textual action categories are tokenized into categorical embeddings. The RGB video image are encoded by the leaf visual encoder, and the RGB video snippet are encoded by the digital video encoder. However, the remote method such as efficient prompt lack the integration between the localization model and classification model. That means that the localization model generated the action proposal and put them into another model. So this makes them the two-state model, which doesn't cooperate between the knowledge between the two models. And for the stable model, uh, how they predict the class does not follow the construction of the clip model. So in our method, we design a dual localization mechanism, not only to determine the proposal boundaries but also to segment the semantic embedding synthesized from clip. And as for the previous method, they both use text from tuning, but in our method, we integrate an efficient fine tuning method known as adapter to adapt a large-scale vision language model to the video domain. So this is the overview of our method. The classification module as the upper part associates the frame embeddings and textual category embeddings from clip encoders to generate the temporal asymmetric embeddings. And the lower part, the dual location, receives the 3D encoded videos snippet feature and passes them to the deformable transformer for last unnoticed action proposal generation. The segment generator is proposed in the dual localization module to dynamically mask the appropriate semantic embeddings for each event. Finally, the selected proposal segment of semantic presentation are aggregated and classified. Finally, we use the adapter as a fine-tuning technique to increase the generalizability of shared classification. So for the classification part, we adopt clip vision module to set up the zero-sum action recognition. Our idea is to fuse each frame embedding with entire set of textual category embeddings, creating the semantic embeddings for every frames. The semantic representation brings the properties of every class for each temporal unit. Multiple action proposals in a video input are assigned with label via segmenting and aggregating related semantic embeddings. This task will be done by the dual localization. So in the dualization module, we adopt the deformable ZEETAD because it requires remarkably less time to train and more importantly, achieves better performance at detecting small objects. This characteristic brings advantage in coping with the vagueness in action boundaries, temporal redundancy in long, middle, and short action detection. you can see we have the three heads output from the deformable transformer decoder. So the first head is about the actioning prediction. The boundary relation head should predict the normalized action to meet the board in the duration of an activity. The second one is the actionist prediction head. Because like for the image object detection, usually use the Gaussian score to rank the duplicate queries, but in here, the 3D encoded snippet feature does not comprehend the strong discriminative power and adjacent frames of an action event share the high similarity with the main ones. So Gaussian score is not a reliable ranking indicator for localization quality. So we adopted the action score to better rank the output from the queries. And the most important one is the segment trade head. So to help us classify an event, so we don't use the start and end timestamp straight from the binary regression heads and the binary segmentation. So we use this based on the max former to reduce the segment that contribute the most to the action on the event. Here we also adopted the adapters called adapt former. So fully fine-tuning tends to all fit to the downstream stack and lose the generalization acquired in the large-scale retraining state of the clip model. So in here we use the adapt-former, which is really require a minimum of parameters to train, but achieve a lot of better performance for the generalizability of the action classification. So this is the result comparison with the state-of-the-art method. You can see like we do the experiment on two datasets from two modes and Ethernet, and on two of the datasets splitting, which is about 75% 25 percentage of splitting and about 50 and 50 percentage of splitting, and we achieve the best performance on the two settings on both datasets on most of the IU's headhome model and achieve far greater performance than the efficient drop and stale model. So to verify the performance of the adapter, you can see that it had the better result than without using it, and better than the text prompt tuning that it used on the stale and efficient ROM papers. So we also verify the way we should input the feature for the model to learn. So the best is to use the I3D feature for the localization model and the clip for the classification model. And building the method at the one-stage model is the best one to integrate the knowledge between the localization module and the classification module. And for the last table, table, we show that like each component of our proposed model framework does help the model to achieve better accuracy, and the most important one is that is the segment generator. So thanks for listening.